So for the last few years, I've been really interested in studying computing spectra, either discrete spectra or continuous spectra from linear problems. And today I'm actually going to talk about nonlinear, or how to compute discrete spectra from nonlinear eigenvalue problems. And this is based on joint work with one of my partners in crime on this, which is Matthew Colbrook. And he actually lived in my house for 6 weeks. And we came up with this idea while we were drinking whiskey. So I hope it's a good idea. Okay, this is not working. Exactly. So the second thing you should know is that I'm Alan's academic brother. These are all pictures of my supervisor and Alan's supervisor, Nick Trefethen, when he completed his PhD. Hopefully this is a picture of Alan close to when he completed his PhD in 1989. But we've had one of those brotherly communication patterns over the last few years. So this is the first email that I got from Alan. It said, "Hi, Alex." And if you have received emails from Alan, he's very good at containing everything in the subject title. And within 2 days, I had accepted an offer at MIT, and it was to work officially under Alan as an instructor here. And I knew he was excited when I accepted the offer because he wrote back "yeah" with an exclamation mark. And I had a great time at MIT for 2 years while I was here. A few months after I arrived here, I got an email from Alan that said 18.06 question mark. And maybe you think like this is arguing about a lunch bill or something. And I remember being very confused by this email. Like, what does this mean? Because I'd only been there for a while. And then about 3 minutes later, Gil Strang and Alan turned up in my office and said, "Would you like to teach linear algebra next year?" And this is where I was. A few months later, I was in this classroom, just fresh out of grad school, teaching 200 kids linear algebra. And I guess that's one of Alan's amazing talents. Apart from he's a great mathematician, he also puts trust in young people. And I had a great time. And I had a good time. And it got Alan and I talking about linear algebra. People, by the way, just some young people. And I had a great time, and this got us talking about linear algebra, and in particular, continuous problems. Infinite dimensional ones, and that's the part of my talk today. So I'm interested in continuous, so these are infinite dimensional eigenvalue problems. They come from applied maths. Here I basically told you nothing because a nonlinear problem isn't really much, it's just not linear. And if you let this T of lambda be lambda identity minus A, then that would collapse to a linear eigenvalue problem. At least a continuous one, as I've written it. And this is kind of the standard process that you might go through in applied maths. You would go to a physicist or someone who's modeled a system, and you've been given an eigenvalue problem. And your first step as an applied mathematician would be to discretize it. And usually in this context, for nonlinear eigenvalue problems, you discretize it typically as a matrix polynomial eigenvalue problem or something similar, because we know how to deal with those from a numerical linear algebra perspective. And then you would use your favorite solver on the polynomial eigenvalue problem, and you would come up with hopefully good approximations to something to do with the physically relevant eigenvalues and maybe, let's say, eigenfunctions of the nonlinear eigenvalue problem. And this is kind of where numerical linear algebra mostly focuses on, is on that step of solving. And part of my talk today is to try to convince you that maybe the discretization step needs a lot more thinking. Because I'm going to try to argue that some of the problems that we've been looking at in numerical linear algebra as test cases for our underlying numerical linear algebra softwares are coming from continuous problems that we've discretized. But the discretization step has already made the discrete problem less physically relevant than we would like to believe. So that discretization step is where there potentially are some issues. And okay, nonlinear doesn't mean anything, it just means not linear, so I haven't really told you anything. But under some, let's say, technical assumptions, that most of the test cases in nonlinear eigenvalue problems that we look at in linear algebra satisfy some extra assumptions which I've made here, which these are just technical assumptions which allow the mathematics that I'm going to do later to go through. So once you've discretized a problem, numerical linear algebra people are very good at solving them. We have software in all different types of software systems. There's hundreds of different packages, hundreds of people have worked on this. In Julia, you can solve it as this is a quadratic eigenvalue problem, which means it has a lambda squared as well as a lambda inside that problem. And you can just solve it in a few lines and get back a good solution. And this is what many people work on. They try to develop methods and then produce software. And Julia is one example that people work in. But if you've already made a mistake when you've discretized a continuous problem, it's too late to do anything about it in the discrete solver. If the discrete problem doesn't have anything to do with the continuous problem that you think you've discretized, then the eigenvalues you compute here might not be physically relevant. And so here's an example of when we try to analyze squeaky breaks. This is a popular example in a linear algebra conference over the last few years, which is analyzing do breaks squeak and how to reduce them. You could argue if you've got the wrong eigenmodes at the end, which has something to do with the frequencies of sound that get generated from these squeaky breaks, then you might blame the model, which means you go to an engineer or physicist and blame them. You might blame the numerical linear algebra people for not solving the discrete problem correctly, but very few people actually blame the discretization. What we do is we use discretizations that we're used to using for solving differential equations, and we just apply them to the nonlinear eigenvalue, differential eigenvalue problem, and kind of just assume that we're good. And often, in the cases I'm going to show you, the discretization step is where the problem is. So there's this standard benchmark. This is a paper which contains 52 nonlinear eigenvalue problems, which has kind of influenced the field in numerical linear algebra, which kind of just goes through and gives 52 physically relevant, mostly physically relevant eigenvalue problems. 25 of those come from discretizing a continuous physics differential equation problem. And so that's over half of those problems are coming from continuous one. And all of the ones that I've investigated have some discretization issues. So about 15 of the ones that I've really looked into, they all have some kind of problem in the step of discretizing. So what kind of problems can you get from discretizing? You can discretize the problem, and you can get spurious eigenvalues, which means the eigenvalues of the discrete eigenvalue problem don't have anything to do with the continuous one that it came from. Okay, they just spuriously put into the complex plane. You can get other problems like slow convergence. You can count multiplicity, so you can get the discrete problem has two simple eigenvalues that converge to a simple eigenvalue of the continuous problem. But if you're naive, it looks like that should be a double eigenvalue. You can get things like wrong pseudospectra, or you can have an ill-conditioned eigenvalue of the discrete problem that was actually discretizing a well-conditioned eigenvalue of the continuous problem. So you can introduce ill-conditioning. And you can get many other things like collapsing onto ghost essential spectra and a bunch of problems that just come from discretizing. So here's some examples of that. So if you take this one-dimensional acoustic wave, this is one example in the collection. And I'm always going to use the discretization that they suggest in the collection. This is a nonlinear eigenvalue problem because of the boundary conditions. It's an acoustic wave problem. It's got a Dirichlet problem at the left end and an impedance boundary condition at the right end. The impedance constant here is 1 as I set it up. And you can go away and discretize this. The standard way they recommend is using a simple finite element method, and you get a nonlinear quadratic eigenvalue problem.
Is I an integer or is square root minus 1?
Sorry? I is a complex, yeah. And so here is the what you get if you discretize, right? So you've got, when you discretize with 10 points and 100 points and 500 points, And you go, okay, is this converging to anything meaningful? Well, no, because the original problem has an empty spectrum. So there's nothing that makes sense here. The discrete problem is giving you back eigenvalues that have nothing to do with the continuous problem, because the continuous problem doesn't have a spectrum, it's empty. So there you go, there's one example of a problem that you might have when you discretize. And it kind of gets worse from here, because you might be able to analyze that one from the continuous problem. But here's the two-dimensional version, so this is just the same problem, but on a square. Now there are some places in the complex plane where the discrete problem just chucks eigenvalues that have nothing to do with the continuous problem. That comes directly from discretizing. And there's other parts in the complex plane where you're getting meaningful answers to genuine eigenvalues of the continuous problem. It's just maybe some of them are converging a little slowly. But this makes it hard. If you actually look at the scales, these two regions are actually sat right next to each other. So it's really hard if you're an engineer and I give you back these eigenvalues to know which ones are physically relevant and which ones are spurious, because they sit right next to each other on the complex plane.
But these spurious ones must be some kind of pseudospectra.
Yeah, the spurious ones are coming from a pseudospectra-like thing in this problem.
What do we really want, right? As you
right.
know,
well, you could say in this problem that the ones that are slowly converging are the physically relevant ones. Right, but as someone who I'm trying to produce software, I want to have correct answers to the problem and not necessarily have to know the physics and know which ones are physically relevant.
so
Yeah.
give them the right answer to the wrong problem, or just the one they asked for?
Well, so I would like to generate software where they can put in the continuous problem, and I won't do the discretization step that's here. I'll change it to a different one, which you'll see. So if you change the impedance constant here to point A, this generates some spectra in a particular place. And this then gets confusing too. So these black dots are simple eigenvalues of the nonlinear eigenvalue problem. The green dots are the ones from discretizations. And what's happening here, maybe you can look on the last one. That's probably the clearest, where it is, right there. You can see two simple eigenvalues of the discrete problem are converging to one simple eigenvalue of the continuous problem. And so you might get convinced that that's a double eigenvalue when it's not. It's just, you've counted the multiplicity slightly wrong from the discrete problem.
Can you say something about the discretization? Are you using adaptive or are you using all the smart FEM techniques you would use?
No, I'm not using, this is not smart. This is non-adaptive finite element discretization P1 on the square. This is the one they recommend in the collection. So out of these 52 problems, the 25 that are continuous, the collection, which is that paper, recommends how to discretize it. And I'm just using exactly theirs without thinking harder than that. You can go for a damp beam. So this is a damp beam held at the ends. The constants there depend on the stiffness moduli and the weight of the beam. You get eigenvalues that just spurious. They don't have anything to do with the two black lines, which are the continuous ones. And if I actually zoom in, so I'm going to zoom in onto that picture right there, which is there. This is something I found really bizarre, which if you look at the eigenvalues, they're wrong. But if you look at the corresponding eigenfunctions, they're resolved. So that's sometimes people would say in some of the literatures here, well, you can always just check the eigenfunctions to see if they've been resolved, to see if you can get rid of spurious eigenvalues. It's confusing. This doesn't happen for linear problems, but for nonlinear, you can resolve eigenfunctions without resolving eigenvalues. So that's bizarre. Here's another loaded spring, and this is an example where you try all your favorite discretization methods, and they introduce extra ill conditioning into the problem, which makes it harder to solve for the eigenvalues accurately. Okay, and it's a very confusing picture. It's hard to know which ones are accurate and which ones are not from just condition number estimation. These black dots, this is my favorite method, the one that we've come up with, and I'm going to tell you about that now. So, if you can't discretize directly, what can you do? How can you even come up with a finite dimensional problem if you're not allowed to discretize? Well, the idea is not to discretize the problem directly. Instead, it's an alternative way to construct a discrete problem. Instead of asking to discretize the operators that are inside your nonlinear eigenvalue problem, how about try to come up with a discrete problem that matches the eigenvalues? So in particular, could you come up with, let's say, a generalized eigenvalue problem that has the same eigenvalues as the nonlinear one, but only in a small region? So a small region that contains a finite number of eigenvalues. So the idea is to replace the nonlinear one by a finite one so that the eigenvalues match in a region of your choice. So this is the idea, and it's not directly discretizing anymore the operators inside the nonlinear eigenvalue problem. But of course, we need a way to compute this generalized eigenvalue problem, the A and the B there. And this gets us into methods in contour-based eigensolvers. So we use tricks in complex analysis like Cauchy's integral formula and things like that to get these matrices. So here's how it kind of works. So step one, you generate a bunch of random functions. Okay, so if we're in randomized linear algebra, we generate a Gaussian matrix here. But we want to use functions for a second, so we're going to just make some random functions. And you test what it looks like on a kind of Cauchy integral formula. If t of z was linear, that would look very close to a Cauchy's integral formula. And you see what comes out. Some more random functions come out. By the way, to compute tz inverse onto functions is essentially a differential equation solve. So you're allowed to go back and use discretization methods for linear system solving on that. Okay, let's call this guy A0. And you do it again on this guy, but with a z added to it, with the same random matrix. You get another random matrix, A1. These are like tall, skinny matrices. And you can show that this rectangular eigenvalue problem right here, just try to, you can make this square if you really want. This guy has the same eigenvalues as the nonlinear one inside the region, inside the contour gamma. And so this is a way to discretize the problem by only using the action of the inverse of the nonlinear operator, rather than discretizing its individual operators like differential parts. Okay, so this is a way to do it. Of course, we're going to have to discretize those functions to make this a practical method and things like that. But we know how to discretize functions, so we can do that. And why do we like infinite dimensional Bain, this version? Well, it converts a nonlinear problem to a linear one. Why is that? Well, Cauchy's integral formula ignores holomorphic functions. And in this case, the holomorphic remainder of the nonlinear term. Cowdish's theorem says that I can write the inverse of a nonlinear eigenvalue problem operator as basically something that looks linear, like V are the generalized left eigenvectors or eigenfunctions, W are the right, and there's a remainder term there, but under some assumptions that's a holomorphic remainder term, which of course gets zeroed out by Cauchy's integral formula. And so essentially, after you do Cauchy's integral formula, the Bain's method is only working on that linear pencil. So we like it because it essentially ignores the nonlinear complications from the nonlinear eigenvalue problem because of Cowdish's theorem. And then you can go and find the eigenvalues of J, which is a matrix. It's a Jordan matrix in general. Okay, so Cauchy's integral formula ignores this, so that's why we liked using Cauchy's integral formula and contour-based methods. It also turns an infinite dimensional problem into a finite dimensional problem because those A0s and A1s, they only have a finite number of columns, and so you can massage that rectangular eigenvalue problem into a discrete one, square discrete one. And instead of computing spectra, the only computation that you actually have to discretize in Bain's method is the action of the inverse onto functions, which when you work with any of these, if any of these are differential equations, those become the differential equations, which we know how to discretize. So basically, computing spectra becomes solving linear systems, or solving differential equations. So we like it for that reason too. And you can actually prove things about this. You can prove that Bain's method doesn't suffer from discretization issues. And this is a pseudospectra inclusion result, which says the generalized eigenvalue problem that you make from Bain's method, assuming you've done the contours integration from Bain's method accurately enough, basically that pseudospectra lives inside the pseudospectra of a slightly bigger pseudospectral sets from T, which basically says you're computing the eigenvalues of the underlying nonlinear eigenvalue problem correctly. This is a with high probability result because remember we use random functions inside Bain's method. So there's a randomized SVD-like analysis flavor to this result. We also have similar results for Feast, which is for linear differential eigenvalue problems, and we have similar results for computing spectral measures which are related to continuous spectra. Okay, so we like these results because this is kind of a robustness result that says we're doing a good job. So if we just revisit the one-dimensional acoustic wave example, I've put an impedance here. Right, if we can discretize this with finite elements again. When I do chi1 for this guy, what does Bain's method give me? The infinite dimensional one. How does it discover that the spectrum is empty? Well, what happens is the A0 and the A1, when you work out the generalized eigenvalue, it collapses to the zero matrix. So you kind of see it, that there's no eigenvalues in any region that you put in the complex plane, because the eigenvalue problem collapses to the zero one. So you can just detect that. If I change the impedance slightly here, then infinite dimensional Bain gets the line, which is they're accurate to what the underlying continuous problem is. And the discrete ones, they still, they do eventually converge to those black, but they converge slowly. So here, when you do n equals 500, that's a quadratic eigenvalue problem. And so in the end, you actually have to solve a 1,000 by 1,000 standard eigenvalue problem to get those yellow dots. So slow convergence sometimes is not good enough even. And here, infinite dimensional Bain does a good job. Okay, so going back to just a word about Alan. So over the years since I met him, and since we had that email exchange in 2014, I've asked Alan for advice a few times. And one time, he gave me this. So I said, I need some advice on something. And he replied, no advice. Just keep doing what you're doing. And actually, he shouldn't have put the no advice there, because I realized at the time that's exactly the advice I needed. Sometimes in academia, you just have to enjoy solving a problem and not worry about everything else, and keep doing what you're doing is a great motto for that. And so happy birthday, Alan. Thank you for all the support over the years. So hopefully I've convinced you that discretizations of at least nonlinear eigenvalues can cause issues. And infinite dimensional Bain's method is a way to overcome that for these discrete spectra. We have a piece of software that has many more examples if you want to see more discretization issues than I've showed you today. Thank you.
Do we have questions?
Want it? No. Okay.
Oh, wow.
So the poor quality of the discretized eigenvalues that you showed up there, I'm guessing has a lot to do with finite element method, and that things wouldn't be so bad if you could do a spectral decomposition with an associated linear.
Right. For each problem, if you spent time analyzing each individual problem, you could come up with a discretization that avoids discretization issues, usually, for discrete spectra. But if I'm trying to build a piece of software, as I'm trying here, that solves nonlinear eigenvalue problems, I don't have the luxury of considering one example after the other. So.
Ready?
Thank you for the talk. Especially the first half, it sounds kind of worrying, all of this. Do you have any real-world examples where you think faulty discretization have actually led to problems?
Or Sommerfeld actually has a few interesting discretization issues. So or Sommerfeld comes up in fluid stability analysis. And some of the eigenvalues, as well as the pseudo-spectra there, are incorrect from the discrete one. Whether that's actually caused anything physically relevant, I don't know, but if you have an example, I'd love to hear it.